All right. All right. Thank you, JD, for the invitation and the introduction. So today I'm going to talk about my current joint work in progress with Wu Chuanyi, who's also in the audience, on profinite transfer maps in KN local homotopy theory. And what do we want to do? So we want to generalize our beloved J homomorphism to higher chromatic heights. And there have been many proposals in this generalization, and today we are going to propose one possible one generalization as a profinite transfer. So my talk today will have three parts. In the first part, I'll review the classical J homomorphism and how to reformulate it in the chromatic language. And the second part, I'll give my first definition of profinite transfers as a dual of restriction maps. And some of you, if you have known some equivalent homotopy theory, you probably know that in many cases, finite transfer maps are dual of restrictions, and we are trying to just extrapolate that to the profinite transfer case. And in the last section, we are going to give a second definition of profinite transfers using a more functorial approach, namely using the six-functor formalism. And in the end, I will explain how to reconcile the two definitions. And in fact, they are equivalent. So that is my plan for today. So without further ado, let me start with reformulation of the J homomorphism. So the classical J homomorphism are the maps of infinity loop spaces. There are two versions, the real version and the complex version. The real version, the source is an infinite orthogonal group. It lands in GL1 of the sphere spectrum, the group of units that Aaron just mentioned in his talk. And there's also a complex version where we start with the infinite unitary group. Well, in this case, it actually lands in the identity component of the sphere of GL1, so it's usually denoted by the Q1S. And the computation of the image of J was done by Adams, and it is closely related to algebraic K-theory of finite fields, which you might think is not really related to today's talk, but secretly it is. So how are those two things related? So when Quinn computed algebraic K-theory of algebraic groups of finite fields, he used this fiber sequence where like the source is the plus construction and the classifying space of a finite field, and then it's a fiber of or it's the equalizer of the map between identity and the Kills-Adams operation. And we know since the bottom map is a fiber sequence of spaces, we can extend it towards left, and that hooks us up with the source of the J homomorphism, and I'll call this map J tilde. So finally the two maps, the JC and J tilde, are connected by the Barrett pre-equivalence theorem that Q1S is also the algebraic K, the connected component of the algebraic K groups of finite sets. Or another model for it is the plus construction on the classifying space of infinite symmetric groups. So in this way, we get a diagram of maps between infinite loop spaces that connects the J homomorphism and the algebraic K groups of finite fields, which will be our gateway to later we'll change it, we'll reformulate this picture in the chromatic language in the chromatic language. Okay, so that's a quick recap of the classical J homomorphism. So now we are going to generalize this, try to put this in the chromatic picture. So let me do a quick review on the chromatic picture for those who are not so familiar with it. So the Adams computation of the image of J is a precursor of what is known as chromatic homotopy theory. And the basic philosophy here is there is a prism of formal group loss elements in the p-local stable stand are organized into families of different wavelengths of periodicity. So here's a picture that I drew. So we hit the beam of the p-local stable elements, and then it splits off into families like height 0 is like you'll see the words like rational ordinary cohomology, rational homotopy groups of sphere, which were computed by Sayre. And height 1, we have the image of J, we have the topological K series that Aaron also mentioned in his talk. And at height 2, you'll see the words beta families, elliptical homology, topological modular forms. And at height 3 and above, you'll see some words, K3 cohomology, topological automorphic forms. don't ask me anything in depth about what happens at height 3 and above. I'm just saying some words that I have very limited knowledge of. So this is roughly how the chromatic picture, the roughly the chromatic picture of stable homotopy theory. And yeah, and to extract the monochromatic layer, one way is there's one way to extract the monochromatic layer is to localize at the Mora K theory of height n. This is only one way. There are other ways to extract the monochromatic information. Here today we are only focusing on the K local category. And a central object of study in this category is Mora E theory. Why? You'll see through its properties. So how do we construct Mora E theory? It is a Landweber theory that we construct using the Lobinitz deformation theory of formal group laws. And it's homotopy groups given by this ring, which is a weight vector drawing a bunch of Power series generators together with a Bott element. And what's nice about it, it is a K-local infinity ring that admits automorphism group by a profinite group. Then those automorphism is like infinity ring automorphism. And a more concrete model, height 1, we can take first Mora E theory to be the P-complete P-complete over the K theory, and then the G1, this automorphism group, is no other than the p-adic units, and the action is the P-complete Adams operations. And why is this? Why is EN ubiquitous in the study of K-local category? That's because first, the unit map from the K-local sphere is a descendable profinite Galois extension. And in fact, if you take kappa to be to be separably closed, then the resulting Mora theory is the Galois closure of the unit in this category. So that's why it is very important. And in particular, Davenant-Hopkins showed that for any close-up group of Gn, we have a profinite descent spectral sequence whose equipage are continuous group homology with coefficients in the homotopy groups of En, and it converges to ENHG. In particular, if we pick G to be Gn itself, we recover the homotopy groups of the K-local sphere. So I hope this convinces you that Mora E theory, it is very important in the K-local category because you can essentially, together with the action by the Mora stabilizer group, there's a spectral sequence we can use to compute homotopy groups of the K-local sphere. Even though it might not be, I mean, we have a spectral sequence, that doesn't mean it is easy or tractable. It might, wait a second, did I lose connection? Because I saw the screens froze for a few seconds.
We can hear you fine.
Okay. Yeah. So okay. With this picture in mind, let's reformulate the picture of the J homomorphism in the stable settings. So passing the diagram we have is a map of infinite loop spaces. And so we can just pass to spectra, and also let's complete the picture of the classical J I prime 2. It's slightly different from the one I show you since I'm doing I prime 2. So now complete I prime 2, we get the following picture where the bottom map here, this is a fiber sequence that we use to compute the K1 local sphere, and the J map. And the J map now stably can be realized a map from this suspension of KO, which is we should think of the spectral version of the infinite orthogonal group to the complete group of units of the sphere spectra. And then this vertical map is the K1 local logarithm map, or that's related to the Bosfield-Kuhn factor. And then there's this map J tilde. So why is this J tilde? So there's a similar picture at odd primes with KO replaced by KU or the Adams assignment. And in this picture, we have this J tilde map. So maybe I should say this. So naturally, we want to generalize the entire picture to higher chromatic heights, but there has been some recent results by Sharka Karmali saying that there's, to some extent, there's a JR map, and I'm showing this picture. There are some obstructions in promoting it to higher chromatic heights. So that part might not be so easy to lift to higher chromatic, but still the rest of the picture, we can lift to higher chromatic heights. And before we move on to that, one crucial observation by Rebecca Hahn and Steve Mitchell is that the J tilde map in this fiber sequence is dual to the Hurwitz map. It is due to the Hurwitz. That's the crucial observation. And at higher chromatic heights, if we consider the fixed points, if we consider the subgroup of Moray stabilizer group, that's the kernel of the reduced determinant, then we have a similar non-fiber sequence, which is related to a correct Westerman's higher analogs of J. So this ENHGN1 sometimes is dubbed like canonical half sphere. It is ZP cross ZP, sorry, ZP got it's a procyclic Galois extension of the canonical sphere, and we have a very similar fiber sequence, just like in height one. So that's a quick review on the classical J homomorphism and how we can reformulate it into the picture of chromatic homotopy theory. And in the next part, I'm going to give you the first definition of profinite transfers as duals of restrictions. So any question before I move on? If not, then let me give you the definition, the first definition. So, given close-up groups of Lamar stabilizer group, we have a natural profinite restriction map from ENHG to ENHH. This is like if you have a representation, of some groups, then you can always embed the fixed points by the larger group into fixed points of its subgroup. So we always have this natural map. And now the question is, we want to define a profinite transfer maps between them with possible twistings. Well, you can say, then what does that even mean? Or maybe I should give you my wish list. So what do I really wish to accomplish by defining, what do I really want in defining such a transfer map? So here's my wish list. The first, I want the target to be ENHG. I don't want to on any twistings on the transfer on the target of the transfer. Second, I want the transfer map to agree with finite transfer maps when H is finite index in G or it is open in G, because for finite group inclusion of in the finite transfer, there's a very natural way to define it. You pretty much just summing up the element, like in the classical term, it's like pretty much summing up the elements in the orbit. And lastly, I want my transfer to be some kind of the J tilde map when G is Gn and H is Gn1. So I want to realize this transfer as a higher analog of J. And okay, so you want to those are all our wish list. We want to, by transfer, of course, we want to flip the direction of the map, and while keeping the target still to be ENHG. So there's a very natural, naive guess, a naive proposal that is, let's just take the dual. Let's just take the dual of the restriction map. And since we want to keep the target to be still ENHG, so let's just take the dual in the category of KN local ENHG modules. And in doing that, the target is still ENHG, but the source is some ENHG like the homomorphisms of ENHG modules. It is something. So in particular, if we take G to be the full stabilizer group, the source is then the KN local Spanier Whitehead dual of ENHH. If we take G to be the full stabilizer group. And that is a case we are going to study in depth. So I don't know, maybe the connection in my from my office is not that great because I've seen like the screens freeze from time to time. So if you lost me, maybe someone, if you can text me, if I really get disconnected, just text me because I might not be aware of that. Okay, so the properties of profinite transfers. So what are the properties? This is our first main theorem today. So consider the transfer maps from the dual of Moray E theory itself, which it has been shown it is d suspension n square of Moray E theory. This equivalence is non-equivalent. This is just saying the dual of Moray E theory is as a canonical spectrum, it is d suspension n square to the sphere. So pretty much in the previous picture, we're taking G to be the full stabilizer group, and we're taking H to be the trivial group. So let's consider the largest possible transfer in our setting. And the properties are the image of the transfer in the canonical homotopy in the homotopy canonical sphere has homotopy fixed point filtration at n square. That's for all heights and primes. Second, when the prime is large enough, when p minus 1 dots don't divide n squared, then the image is precisely the filtration n squared line. Because it's under this assumption, the homotopy fixed point spectral sequence will have a horizontal vanishing line at s equals n squared on the E2 page. So this is indeed the top filtration. This is indeed the top filtration. So those first two bullet points, I sort of identify, I just give you some description of the image of the transfer in the homotopy group of the canonical sphere. Okay, I mean, why I'm calling it transfer? I mean, this is just some maps that I defined. So if by saying transfer, you definitely want to ask, how about double coset formula? Because for finite transfer and restriction maps, double coset formula is a very important. Those are very important formulas. So, well, what happens if we compose restrictions and transfers? Turns out, if you first do transfers and restriction, you'll get a lot of zeros. For any closed subgroups of GN1, the kernel of the reduced determinant, if we compose transfer, then restriction, this map is always zero. In particular, this applies to all finite subgroups of GN. So that's first transfer, then restriction. Recall if it were like finite transfer, if it's like finite transfer, if you transfer from the g fixed point to the entire thing and then going back to the g fixed points, that's usually multiplication by the group order. But now it is zero. I mean, you can take f and f prime to be the same, and yeah, it is zero in this case. Lastly, the other way composition, if we first restriction, that's it. That's like we send the d-suspension n square of the sphere to the d-suspension n square of the Morat E-series, and then we follow that by transfer. Then turns out this is sort of a Poincare duality map in the sense that it sends one in the source, in the homotopy source, to the product of this exterior algebra generator of the rational homotopy group canonical sphere computed by Bartow, Schrank, Stapleton, and Weinstein. So the takeaway here is one for double coset formula, at least in the cases I'm displaying here, restriction followed by transfer, that is zero a lot of times, and then transfer followed by restriction, it is zero a lot of times, and restriction followed by transfer, it is a multiplication. It's like multiplication by an orientation class. Okay. So now you may wonder, okay, how can we prove this? How can we prove this? So the first, the proof goes by the following. So when you prove a result like this, what you can do usually, sorry, did I lose connection or is it okay? So when you prove some results like this, usually you start with, oh, that's because Morat E-series satisfies this or that nice property, so we have such a claim. When we prove this, we start by observing the failure of the Morat E-series satisfies a certain property. Namely, for any spectrum, you always have a natural map. This way, like going like E tensor the dual of E to its endomorphism ring. If Morat E-series were dualizable, then this map should be an equivalence. But turns out, as a Profinite Galois extension of the source, Morat E-series is not dualizable as a canonical spectrum. And in fact, this map, it might even be pi star 0 in odd heights. It is pi star 0 in odd heights. But then, nevertheless, there's a natural map connecting them to going back to Morat E-series itself. In the top, we have the Morat E-series tensor. It's like base change of the transfer map we defined by Morat E-series. In the bottom, it's a dual restriction map. And this diagram, even though I'm saying this vertical map is not an equivalence, but in any case, this triangle is GN equivariant, and that means we can take contour fixed points by the action of the stabilizer group. And turns out the fixed point of the source and target of the vertical map, now miraculously they are the same. They are both the dual of Morat E-series. And moreover, this map, after taking homotopy fixed point, is an equivalence. And what's good about that? Well, if you want to study what happens to the transfer map in homotopy fixed point spectral sequence, you might really want to use the top map, the top horizontal map. But as we'll see in a moment, it does not really tell you much information. But now that we know the bottom map is related to the top map by an equivalence, so we can study what happens to the transfer map in homotopy explain spectral sequence through this endomorphism ring of Mora E theory. And that's where the magic happens. So let's analyze the source and target of this vertical map. It is a result of Baudry, Gors, Hopkins, and Stronowska, and a recent preprint by Dustin Clausen, where they identify the equivalent homotopy type of the dual of the Mora E theory. And it turns out it is a co-induction. It turns out En tensor Den using their results, it's a co-induction of the dual itself. And since it's a co-induction, actually it doesn't matter if we're saying Den is a GN equivalent spectrum or it's just trivial action or non-trivial action. It doesn't matter since it's co-induction. But since it's co-induction, so actually the group cohomology on this co-induction is concentrated in degree 0 by Shapiro's number. So if you're only looking at what happens to the transfer map by base change by doing the En-based Adams-Novikov spectral sequence, you are only saying, oh, the source has Adams-Novikov has homotopy fixed point filtration 0. But that doesn't really tell you much information because if you have a map between spectral sequences, there are always filtration jumps. You can jump from 0 to anywhere. So this contains, very little information. But whereas the bottom, it has been identified by result of Barron's Davis, Harvey, and Strickland that the endomorphism ring of Mora E theory is a complete group ring on the Mora E theory. And using Poincare duality and Shapiro's lemma, we can see that the group homology of this endomorphism ring is concentrated in degree n squared, which is the virtual cohomological dimension of the small stabilized group Sn. And now, if you look at the bottom map, and what happens to the homotopy fixed points, the induced map on the homotopy fixed and the bottom map, the source already has homotopy fixed points filtration n squared. So the target, whatever it hits, it must have filtration at its n squared. So that's how we prove the first part of our theorem, namely the image of the transfer in the canonical category has filtration at its n squared. Because by changing the source, by using this endomorphism, by using the bottom map to model the induced map on homotopy fixed point spectral sequence, we can already say the source already have filtration n squared. But if you just start with the top map, you just say, oh, the top map, is homotopy fixed point filtration 0. And because of filtration jump, you don't really have much control about where the filtration of the target. You don't have much control over that. And how about the surjectivity part? How about when the prime p-1 does not divide n? When the p-1 does not divide n, then the Sn, the small stabilized group has homotopy fixed point structure, have cohomological dimension n squared rather than just virtual cohomological dimension. And then you can study with the induced map of the bottom as due of the restriction in group cohomology. And it hits Hn square of Gn, the top 9 in the homotopy fixed point spectral sequence. And because of Poincare duality, this H sup n squared is also is isomorphic to H lower 0, which is the orbit space. And you can check the induced map. This composition is a projection onto the orbit space. So hence, in that case, this the transfer map the transfer map surjects onto the top filtration of the top homotopy fixed point filtration of the homotopy groups of the canopsphere. So the crucial observation. So the proof really relies on this triangle, this observation that we can, instead of just doing like base change, studying the transfer map and the induced map in the EM-based the Kobar complex, the armature complex. Instead, we go to the endomorphism ring, and turns out that that's a better. From there, that we have much better control on the image of the transfer. So that's the first half. That's a proof of the first 2 bullet points on the homotopy fixed point filtration of the image of the transfer. Any question before I move on to the double coset formulas? If not, then let's move on to the next part, the double coset formula. So the transfer maps and the restriction maps, they are natural with respect to they are natural with respect to the group extensions. So given oops, I don't know what's happening with my zone, so somehow something is not quite right. Let me do this, and maybe things will get better. Uh, yes, so if you have any closed subgroup of GN1, then this composition factors through the zero map, where this zero map in the box, where this is part of the fiber sequence for that fiber sequence of the fixed point of like that we can use the half sphere to compute the homotopy group of the canonical sphere that I showed you earlier. And for finite subgroups, any groups of finite order in GM must have the determinant must be a root of unity, hence it must be in the kernel of the reduced determinant. So that proves the first half. The transfer followed by restriction, it's at least for closed subgroups of GN1, that's always going to be zero. We don't know for general closed subgroup GN if this composition is zero. Because I mean, if it were if we are doing just finite transfer and finite restriction, then it's probably not going to be zero. So we don't expect this such composition is always zero, but it is in this case it is zero. And next, for the other composition, so we can keep track. So pretty much the proof is going by keeping track of what's happening on the group cohomology. If you do the other way composition, then by the result of Bartow, Schlank, Stapleton, and Weinstein, we know that the group cohomology of Gn, rational group cohomology of Gn with coefficient in pi star En is actually the same as that in the coefficient of the rational wave vector. And there you can say this composition we are writing is essentially the same. It is the same as the Poincare duality map, and in particular, it sends one-to-one orientation class in the top degree group cohomology. So here I'm only saying things are like it sends to some orientation class, and also in the BSSW paper, those zeta i's, they are the exterior algebra generator of that rational Lie algebra cohomology. So it is so I don't know if there are integral constructions of zeta I. So I'm saying it is just sent to some orientation class. It might not be the same as some particular construction that you got. And in particular, at height 1, if you do the transfer from the desuspension of Ku to the K1 sphere, you are not going to get the actual zeta 1. You are only going to get twice zeta 1. You are only going to get twice zeta 1. But still, the claim is saying this is true rationally, so that's fine. That is fine. Okay, so
Sorry, can I
this
ask a
is a
question about the first bullet point?
yes.
So in that factorization, how do you know that the transfer followed by restriction in the box is zero? Sorry if I missed it.
That's because we have this fiber sequence of. Okay, there's a caveat. The easy the way to the way maybe an easier explanation is we have this fiber sequence realizing Kn as a fiber of the map between En HGN1 and it's like the some Adams operation -1. And then if you extend towards left, then you get that. But there's a slight caveat. Yes, if you extend towards left, you get desuspension of ENHGN1, which is a desuspension, which is a dual, of ENHGN1. But you have to prove that the map is also the dual. So there's some caveats here.
See.
Or if I go back to really far, yeah, it is related to the sequence in the bottom.
I see.
Yeah.
Okay. Thanks.
Mhm. Okay, so we have identified the image of the transfer as top when the prime is large enough as the top filtration in the Hubble fixed point spectral sequence. So you may ask, how much has that been computed? Well, when so Dominic Carver and I used Gross-Hopkins duality to compute not the group cohomology itself, but we modeled by some pretty large ideal. But you might notice we didn't model by UN-1. We didn't model by UN-1. Essentially, we're using the Minimarna-Wilson computation and then use Gross-Hopkins duality to bootstrap to this case. And I talked about this computation, I think 4 years ago, also in the ESHT research seminar. And moreover, there are not even non-local elements in the stable stem detected by KN local transfer map. In 1982, I think, Oka and Shimomura proved that at height 2, prime greater than 5, they are related to the PP relative families in Adam's local filtration 4 detected by the K2 local sphere, or really K2 local Smith-Stoddard complex. And since those are filtration 4, so after K2 localization, they are still in filtration 4. So in particular, those elements are detected by the transfer. And also, maybe another thing to notice is those beta, since those beta family elements, they have you can construct them using cell using out of finite cell complexes. So those are naturally permanent cycles. It's just we don't know if that's zero in the stable stem, but Oka and Shimura prove they are not. So from their result, we can say at least at height 2, prime greater than equal to 5, our transfer F does say something that was that's the classical J does not say, because the classical J only says things in Adam's local filtration 1. Okay. And also, another thing is not only can we transfer those atoms, we can also transfer differentials. So let me showcase you with one example at height 1. So, this is a picture of the homotopy fixed point spectral sequence to compute the K1 local sphere at prime 2, which is a fixed point of Morat series, first Morat series by Z2 cross. And you notice I have color labeled all the dots and arrows by 2 colors. So those in teal color, they are from the restriction, namely they are from E1HC2, namely KO. And then there's another copy that is from dual of KO. And I'm here just superposing into the same picture. Of course, this is not going to give you the K1 local sphere itself, since K1 local sphere is not a direct sum of those two of KO and the dual of KO. Well, they are related by this fiber sequence, just like what we've seen earlier. And if you compute the induced map of those two induced map of those two spectral sequences on their E2 pages, and then you just plug in all the differentials, and yes, that is the entire E2 and the E2 page and the D3 differential of the homotopy fixed point spectral sequence to compute the K1 local sphere at prime 2. And here I'm saying all the differentials, they are either from the transfer, aka the Hurwitz map, or from either from the restriction, aka the Hurwitz map, or from the transfer. And by doing that, we can completely determine this spectral sequence. Except there's slight caveats. There are some extension problem on the invalid page. Say here there is an extension problem. And yeah, so that's another way I want to showcase how potentially this transfer maps might be useful in computing the profinite descent spectral sequences at higher chromatic heights. And I have 12 minutes left, so
Can I ask
I
one
want to
quick
switch.
question about that chart, just to
Yes,
test my understanding?
yes,
You mentioned the
yes,
hidden extension at 3,1 up to
yes,
3,3, and that's like
yes,
eightfold periodic, right? Like if I look at minus
yes,
5,1, I see
yeah,
these
yes,
things.
yes, yes, yes.
Thanks.
Yeah, so in the last part, I want to switch gear to a more formal definition of profinite transfers via the six-functor formalism. So yeah, I guess as nice as the results I was describing earlier, it's still it's kind of an ad hoc definition. We're just saying, oh, let's just take the dual restriction and see what happens. And yes, there are some nice results, but classically for finite group for G equivalent homotopy theory, especially for finite group G, the transfer maps can be defined more functorially. And like if you will like genuine G equivalent spectra in the language of spectrometric functor, then you should start with like the span category, blah blah blah. And here I'm saying, oh, this is a profinite transfer. So can you make it more functorial? Is it really the profinite transfer, or is it just a profinite transfer? So let me give you another definition of profinite transfer, and then I'll show you why they are equivalent. So we are going to use the six-functor formalism following six-functor formalism. And here's a recap of the definition of general six-functor formalism. So the setup is, let's say, be an infinity category containing all the limits, and E be a class that's stable under all isomorphism and stable under pullbacks and compositions. Such a pair, C comma E, is called a geometric setup. So to get a six-functor formalism, abstractly, we will start with three-functor formalism. And this is a Lax monoidal functor from the correspondence category to the category infinity categories. And this correspondence category has objects the same as that for C, and the morphisms are those zigzags where we require the second egg, this G map has to lie in E. And the composition is given by the pullbacks. And so here, due to space, I'm not drawing how the composition works. And also, it is because of the composition requirements that we require that E is stable under pullbacks and compositions. So given this, we can define the three functors. For each D of S, there's a tensor product. There's a tensor product there. There's a monoidal structure. That's the first functor. Then we have the pullback, which is the induced map. Since this is a Lax monoidal functor, it also induces some.
Now I think we finally did lose him.
Yeah. Oh, we can wait a minute, see if he gets back. Send him a text since he asked us to. I'll pause the recording. Oh, hi, Ningchuan. I think you dropped out
Yes.
for about 20 seconds.
Oh.
So
where did I?
we were just talking about the F upper star.
Okay, F upper star. Okay. Okay, F upper star. And yes, if we consider the induced map of D on the other zigzag, we get the G lower shriek, but this G is necessarily in E. So in the classical algebra geometric setting, you should think of F upper star as a pullback of Schiff's line bundles, G lower shriek as those exceptional push forward, or another way is to say it is also sometimes goes by the name of cohomology with compact support. And to get the six-functor formalism, we just double the three-functor formalism by saying the three functors, they have right adjoints. And this is a more formal way of defining the six-functor formalism in the negative infinity category that I learned from the notes of Peter Schulze. Okay, so in the theory part of this project, Guchuan and I, we import the Heyerman six-functor formalism and smooth representation of PID groups to the K-noble category. And what does that mean? I'm not going to go through the details. So in the setting here, the geometric setup C is a category of condensed anima. Don't be scared by those words. It probably doesn't mean much. I'll tell you how to think about it. D of a point is a category K-noble spectra. And the D of this stacking quotient of G, so G is a p-adic Lie group, you should think of it. And then the star double quotient G, you should think of it as a continuous classifying stack. You should think of it as a continuous classifying stack. And we're saying the value of D on the continuous classifying stack is the category of continuous smooth G representations in K-local spectra. Where smooth here means it is any spectrum is smooth if a spectrum is equivalent to its colimits by its colimits by open subgroups of G. So I'm using this notation sub O to mean open subgroups. In particular, by the theory of Devenant-Hopkins, we know Mora E theory itself is a smooth representation. And yes, there's a classical definition of smooth representation, and here we are sort of having a derived smooth representation. It's really a derived smooth representation. And so how about E? Because E is a class that we can do all the Schrade functors. I don't know precisely what E is, but I can say that E contains at least all continuous maps between profinite sets, which are a full subcategory of condensed anima, and as well as those between classified stacks of closed subgroups of Mora stabilizer group. For those ones, we can define the Schrade functors. And how do we think about those functors? Well, for those maps between classified stacks induced by inclusions of closed subgroups, then this adjunction I lower star upper star is a co-induction restriction adjunction. And for those induced by quotients or surjections of this profinite groups, this adjunction P lower star P upper star is a fixed points inflation adjunction. And finally, in our case, for everything in E, lower Schrick is the same as lower star. And that is to say everything E is kind of proper. So now I can finally give you the formal definition of profinite transfer. Consider this diagram where H is a subgroup of G is in Gn, and we have this diagram in condensed anima, or if you don't like condensed anima, just it is a diagram of classifying stacks. Then the profinite restriction maps can be realized as a map induced by the unit map of the adjoint pair. So let's go through this a little more carefully. In the source, we have Mora E-theory. IG upper star is a restriction, so we are forgetting the action on E. We are restricting the action to just a subgroup of Gn, and then PG lower star is the homotopy fixed points. So that's a source. So the source is ENHG. The target here, if you compose this F upper star, IG upper star, then this is restriction all the way to H. So you are just forgetting the action to the subgroup H. And then it's PG lower star, F lower star, the composition is PH lower star, so you are taking the H fixed points. And then you get a map, and then those two are, you get a map between them because there's the unit map of the adjoint pair. So there's another adjoint pair of the Schrick functors, and that is, we are going to say that's a formal definition of transfer. So the hot definition that I gave earlier as a dual restriction is equivalent to the map that induced by the co-unit of the other adjoint pair, the F lower Schrick, F upper Schrick. So, so why is that the case? I only have 3 minutes left, so let me quickly go through the last slide. So the observation is, how can we show this? So the slogan is, in the smooth representation category, profinite restriction is a co-limit of finite restriction. And then that means profinite transfer is a inverse limit of finite transfer. And for finite transfer and finite restrictions, it is a classical result that they are dual to each other. So roughly is the key slogan of this proof. So first, similar to what I told you earlier, the Devenez-Calkins shows that the ENHH, you can realize that as you can approximate it by some homotopy fixed point of open subgroup of G. And in the ENHG module category, each ENHU is self-dual, and the finite transfer is dual to the finite restriction map. And now let's denote this inclusion of classifying stack by FU. Then the finite restriction map, the finite transfer maps, it is equivalent to this map induced by the co-unit of the Schrick adjunctions. And now this is a part I was saying earlier. In the smooth representation category, we have a natural isomorphism between the co-limit of finite restriction. So you should think of this like forget and then co-induction. This is like we first forget to the U action and then co-induce back to a G action. And this is a natural isomorphism. So by adjunction, we get another equivalence of functors of between the Schrick, this component, the F lower Schrick, F upper Schrick. This is pretty much what I was saying earlier. The profinite transfer is the inverse limit of finite transfer. So combining the above, we get a sequence of isomorphisms. So here in the first step, I'm writing ENHH as a co-limit of fixed point by open subgroups of U, by open subgroup of G. And then I'm pulling out the co-limit to become a limit. And this is like the dual of the finite restriction. The dual of the finite restriction is the finite transfer, which we can express in terms of Schrick functors. And the inverse limit of the Schrick functor, it is the F lower Schrick, F upper Schrick. So in that sense, we reconcile the two definitions of profinite transfers. The first is a whole definition as a dual restriction. The second definition uses the six functor formalism of Hare and Mann on the smooth representation of p-adic Lie groups. And I think I'm out of time, so let me just stop here. Thanks for your attention.